Good. Hello, everyone. Welcome to this week's ZocMap. Today we have Sergei with us, who's a third-year physics student here at ETH, and he's going to be talking about magnetic reconnection from theory to applications in computer simulations. Please welcome him.
Okay. Hi. Okay. First of all, thank you for giving me this opportunity to share my research, and I'm also very glad to see a lot of people here. Maybe to quickly say something about all those signs. So in the end, mostly I'm going to be talking about work that has been done with the institute at the Helmholtz Institute in Dresden. And so I would also like to mention my two collaborators here, which is Klaus and Richard. So they have an equal share in this work. And also in cooperation with the Kasus Institute, and we're using PIConGPU, and it's all part of the Plasma FEPSI collaboration. So now that I'm done about talking all the institutes, let's actually get into the topic. So initially it was just meant to be magnetic reconnection, which is this plasma physics phenomenon, but I thought it doesn't make any sense without talking about the plasma physics behind it. And so the topics, they changed a bit. And so now what I'm going to do is I'm going to walk you through a very, very brief and probably not extensive enough introduction on plasma physics. Then I'm going to talk about how you numerically simulate plasma physics, which in many cases are particle and cell simulations. Then we're going to talk about what magnetic reconnection is, and then we're going to talk about what this research is actually about. It's understanding magnetic reconnection through radiation that you kind of can measure from or in space. Okay, now, so what is plasma? Well, plasma is this kind of soup, which you see here, which is made out of negative and positively charged particles, which most of the time have equal share, and they're all together. And so if you look at it from very far, it's basically neutral, right? So most of the time it's compared to fluids or gases, it's low density. And then you say, okay, like when you look from it on the outside, it's like a normal fluid. But then once you go on the inside, you can see your charges, they're kind of separated. So you kind of also have to care about electrodynamics, because on the microscopic scales, these things move and they create electromagnetic fields. And so, of course, that also influences your motion. So to get a better feel of what plasmas are and what the orders of magnitude are in which they appear, I have this graph here. I hope it's fine that it's in German. Probably it is. But on the x-axis, you can see in logarithm the number density of the particles in the plasma, and on the y-axis, you have the logarithm of the temperature. And so this red line is room temperature, and what this is supposed to showcase is that in many cases, especially in astrophysics, these plasmas, they take place in temperatures which are way above what we experience here on Earth. But you can also see that actually happening on Earth in the ionosphere or in flames, where flame is actually just plasma. And the ionosphere is actually quite interesting, because there you can see the plasma happening live in action. Because when you see like these auroras, that is actually just the plasma phenomenon. That is a lot of charged particles gyrating in the Earth's magnetic field, emitting radiation. And so you can actually see plasma on Earth, so it's not just like some very far away, distant, strange phenomenon. Okay, but in this talk, we're going to actually focus on solar coronas, which is where magnetic reconnection happens most of the time. And here you have a number density of approximately 10 to the 15, and around 100 electron volt, or in our case, around keV temperatures. So 10 to the 15, a number density, you might know, you might not know, it's actually the order of magnitude of just gases. So, as I said in the beginning, looking from far away, we'll kind of have to think about fluid dynamics, because we kind of want to model gases. But as I said, also in the beginning, it's just half of the story, because on the microscopic scales, we have to care about electrodynamics. And two of such examples where very characteristic length scales or time scales emerge in plasma physics, I can give you here. And they emerge through really looking at the microscopic electrodynamics. So let's first focus on the left-hand side, where we talk about the plasma frequency. And the plasma frequency, what it is a characteristic timescale or characteristic frequency for a plasma which is in thermal equilibrium. So any plasma which is just there and you don't touch it, it will oscillate in this plasma frequency. Well, why is that? Now, we've talked about the soup earlier, and the soup had like this homogeneous density in particles, but it also had a temperature, right? So it will move in random directions, and because it moves, you can have arrangements where randomly in a small subvolume, you'll have more positive charges and more negative charges on one and the other side. And so, because you kind of separate charges, this will give you an electric field. And by linearizing Maxwell's equations, what you'll get is that this electric field is just proportional to the distance and separation. But that, of course, also means, well, we have the electric field, let's just write the equations of motion, which is m times a is equal to minus E times the electric field, so minus charge times the electric field. And that, since the electric field is proportional to the separation distance, you'll get m times a is equal to something proportional to the distance, and that is a harmonic oscillator. So you'll see that, again, what I said in the beginning, a plasma in thermal equilibrium is governed by some harmonic oscillator behavior. And so this harmonic oscillator behavior is exactly the plasma frequency. So keep that in mind for later, because we'll need it at some point. Because remember when I said in the beginning that we're going to talk about radiation, the cool or not so cool thing about this plasma frequency is that if you generate any kind of radiation inside the plasma below this plasma frequency, it won't escape the plasma. So anything you measure in space coming from there in terms of radiation, anything you measure will not be below the plasma frequency. So any signals you see with a frequency below the plasma frequency, it's like you're not going to be able to measure them. Now, okay, so this was on time scales, but let's look at length scales. And another very characteristic length scale is the Debye length. And the way to think about it is the following. So take this positively charged particle Q. It has some positive charge, and you insert it in a plasma. Now, because it's positively charged, it will attract all your negative charges, and they will kind of surround this positive charge in sphere. But this positive charge has some Coulomb potential. And because it's surrounded by negative charges, which kind of shield this Coulomb potential, your Coulomb potential will be weakened. And so you can see on this right-hand side a plot of this Coulomb potential, where you can see on this vertical axis, the more you go away in radius, the weaker this Coulomb potential becomes, this shielded Coulomb potential, compared to the actual Coulomb potential, which the charge would have without all these electrons surrounding it. And so the Debye length, this lambda d, is the distance after which you basically don't have to care for this Coulomb potential anymore. So the Debye length tells us something about if you go enough far away from a positive charge you placed in a plasma, you don't see that positive charge anymore. And that is actually referring to what I said earlier. When you go in close enough, you care about electrodynamics, but far, far away, your plasma is just a gas, it's just a fluid. And these two length scale, time and length scales, the plasma frequency and the Debye length, they go to show this. Now, so we've gotten a bit into the mathematics and how we describe plasmas, but there is a more rigorous framework, because you cannot always look at such individual particles, especially when you have complex dynamics where there's a lot happening in different regions in space. So the question is, how do we describe this mathematically? And there's many approaches, and one of such is a kinetic approach, meaning one coming from statistical mechanics. And so the first equation many of you have seen, it's, in plasma physics they call it the Vlasov equation, but it's basically the Boltzmann equation without a collision term. For those who have not seen it, F is your distribution of particles in phase space. So from F you can not only infer what density do your particles have in which point in space, but you can also think about, okay, actually how many particles do we have of a certain velocity? And this overall equation, the way you can think about it is it's a continuity equation, but a continuity equation in phase space. So what comes in, comes out, but in phase space. And now maybe a short notice on why is it justified to say that we have no collisions in a plasma. It's actually not justified for all plasmas. Sometimes you have to think about collisions. But if you start calculating, especially with low densities as we have it in our solar corona case, remember 10 to the 15, which is a gas case, then you'll quickly find out that the frequency at which a collision happens, it is much lower than our plasma frequency. And to interpret this physically, it's just saying that, well, before anything collides in your system, something else will happen, and you'll have to care about other effects. So this is the first equation. And you might have noticed it's much more general. It's kind of for gas or many body systems. And then let's talk about the other equations, which you're probably familiar with, which are Maxwell's equations. And so this is all you need. You need to think about how does a many body system behave when we think about electrodynamics, which is down here. But what you'll also see is that it's very complicated to solve, right? You have one time derivative, 3 spatial derivatives, and from this Boltzmann or Vlasov equation up there, you have another 3 velocity derivatives. So it's like 7-dimensional in derivatives. And then you say, that's kind of harsh to solve. Let's actually look at particles individually again. Now, if you look at particles individually, you'll quickly notice that's even worse, right? Because we have 10 to the 15 in number density. So if you go like into 1 square meter of volume, and astrophysical systems can be much, much larger than that, you'll have to solve differential equations for 10 to the 15 particles, which is computationally not feasible, and also not like, try doing it by pen and paper, that won't work. And then you go, okay, fine, yeah, let's go back to this. And then you say, so the way you would normally solve differential equations, partial differential equations, is you would discretize them. So you'd say, let's not take a derivative, let's make the spatial distance finite. But that becomes also horrible, because you have to do this in 7 dimensions. And so you kind of need a different approach. And one of such approaches we'll examine now, for which we need kind of a theorem. For all of those of you who have heard quantum mechanics, this theorem is basically just the Ehrenfest theorem, but a bit differently. So what you do is you say, well, I'm not interested anymore how really F is going to look like in the end or throughout time. What I'm going to be interested in is how everything in my system looks on average. And so what you do is you say, okay, I care for my X, so my position on average, so how's the plasma going to move in position on average, and I'm going to care for what's its average velocity. And so the way to derive this is you multiply it by x, then integrate over phase space, and you get one equation, and then you multiply it by v, you integrate over phase space, and you get the other equation. And the steps to that are not important. What is important is this. You get exactly your basic equations of motions, where you say the time derivative of the average position is the average velocity, and the time derivative of the average velocity is your average acceleration. And you can say, cool, wow, okay, we know how a plasma moves on average. And it moves exactly like a charged particle. And that already kind of gives us a hint, well, how can we approach this to solve this entire problem? We could think about it, let's not care for too much detail, let's think about averages. But you might also say, well, thinking about averages is not going to bring you very far, right? So if in different volumes of space, there's different plasma dynamics happening, your average is going to not tell you anything. But again, we can be smarter than this. What we can do is, first of all, focus on the left-hand side. And on this left-hand side, what you see is a lot of red dots. Now, these red dots, they are so-called macroparticles. And macroparticles are not just single individual particles, but they encapsulate multiple particles, thousands or even more particles. And then for each of those particles, because we know on average they will behave like a charged particle, you will only solve this equation of motion for a single charged particle. So when you have 10 to the 15 particles, instead of actually looking at 10 to the 15 particles, you look at only 1 million. Or 100 million, because you encapsulate multiple particles in a single macroparticle and solve the equation of motion for that macroparticle. Okay, so these are the red dots, but you might say, aha, we can look at the behavior of a single macroparticle, but once we shift macroparticles, kind of your electric field will change because you have charge separation. And so we kind of also have to think about, well, how do your electromagnetic fields behave? And so what we do for that is we also look at a grid. Now, I told you earlier, partial differential equations can be solved by discretizing space. So instead of taking derivatives with the spatial distances going to 0, you make them finite. And so this introduces this grid. And so to simplify things, we say the macroparticles, you look at it in an average behavior, so it moves around like a single charged particle. But the grid, this is there to solve Maxwell's equations based on the motion of the charged particles. And this gives you kind of a loop, right? Because every time we solve something numerically, we want to do it iteratively. For each time step, we want to have this iterative behavior. So you can see on the top, this blue term, it says, aha, let's first solve our equations of motions for these macroparticles. So you shift them in time. Then the next step is you say, okay, now we have this configuration of charged particles. That means we're going to get such and such a charge distribution. And then based on this charge distribution, you can solve Maxwell's equations for that time step. And then from Maxwell's equations, you get the force, and you do that over and over again until your solution evolves in time and you get some kind of cool plasma dynamics, which you want to see. And so this is how you simulate plasmas. Now, we do this with this code, which is cut off here, so let me go back, with this PIConGPU code. And PIC stands for particle and cell, and on GPU are graphic cards. And what is so special about this code, let me do a bit of Werbung, yeah? So special about this code is that it's very, very high performing. Like, it's not like I've worked with many, many other codes, but this is like one in a kind. It's a bit hard to use, but it's very rewarding because you can parallelize everything and get huge simulations, which you'll actually see a bit later. Okay, and so this code has another special feature which we're going to need for later, right? So we talked about, nice, we can look at cool plasma dynamics and look how all the charges look. What this code can do as well is actually calculate your radiation. So once your plasma moves very abruptly, you'll get a lot of particles being accelerated, and you know the charged particles that are accelerated, they give off a lot of radiation. And the way we calculate it is the following. So imagine you have a charged particle, so a particle with charge Q, which moves with some velocity beta at some points in space r. And this radiation, the emitted radiation from that particle, is governed by two terms. So there will be a term which comes from just the velocity of the particle. So if a particle moves with a constant velocity, it will emit this kind of radiation. And then there's also a term which comes from the particle actually being accelerated. But what you'll find out if you look at really the raw expressions for these terms, which are not very interesting at the moment, is that the velocity term squares with 1 over r squared. So the further you go away, it scales with 1 over the distance you go away, 1 over the distance squared. But the acceleration term, it scales not as quickly. It scales only with 1 over r. And so in astrophysical systems, usually you'll be very, very far away. And so what that means is that if you're very far away, because your velocity term, it gets smaller quicker, you say, we don't care about velocities. We only care about acceleration. And so this gives you a very, very big term on the right-hand side. Now let's talk about this big term because there's some interesting and important features about it. Now, first of all, what you see is that this term incorporates a Fourier transform. Why is that? It's because in the end, when we look at radiation, or when we want to analyze radiation, we always want a radiation spectrum. So we want on the x-axis the frequency, on the y-axis the intensity, so we see, we have a peak at a certain frequency. And that you get from a Fourier transform. Now, the term in the middle is the Lennard-Wiechert potential. That is actually the expression for the radiation you get from an accelerated particle. And that is not too important. What is important, however, is that you can see there's like an n cross whatever. And this n is the direction vector, so the direction from which you're looking on the particle. So when the particle comes at you, you'll see different radiation emitted than when the particle moves in a different direction relative to you. And so this will be, again, important for later when we analyze the data. And now finally, of course, I talked about now a single particle moving, but in plasma physics we have a lot of particles. So we sum over all particles. And PIConGPU has an interesting trick to that, because I told you earlier we do 100 million particle calculations or even more. And that's not 10 to the 15, but that's still a lot. And actually calculating this giant term for 100 million particles, that's just not feasible. So what they do instead, actually, they take these 100 million particles and take a random subset of the particles and only calculate it for this random subset. This is not too interesting, but this is just a fun fact, because maybe you're interested in high-performance computing. Okay, and what you get in the end is this. Here in the middle you have some, what looks like a sponge, it's actually a plasma. And then on the outside, you measure radiation from each angle, and you get such a spectrum. So the depth of this dome is some frequency. So if you just look at it from this axis, you would see some kind of frequency spectrum. But then you can measure it from different angles, right? You can measure it from the azimuthal angle and the polar angle. And this is why you get this kind of spectral map, which looks like a half dome. And why is this interesting for astrophysics? This is interesting for astrophysics because you never know from which direction your radiation comes in astrophysics. That to say is that if you want to kind of say, aha, we want to understand some astrophysical phenomena through its radiation, you always have to understand every direction, because once you place your detector there, you don't know which direction it's coming from, and you can only say, aha, it's this and that phenomenon, if you really know every direction. Okay. So before I continue, maybe I'll give room for questions. Yeah?
Yeah, I have one question. So essentially, at the beginning, you were showing the Lassov equation,
Yeah.
which essentially is just a continuity equation.
Mm-hmm.
And then you said, okay, we do average over all particles,
Mm-hmm.
we do the stuff with vector particles,
Yeah.
and so on. So where does actually interesting dynamics occur? How does interesting dynamics take place just from the equations of movement, essentially?
You mean the average equations?
Yeah.
Okay, so this is where this particle and cell comes in. So the reason why I said it's not very interesting to look at only the average, and I think that's what you meant, right, is because you get the average. If you have different things happening in different volumes, it's kind of, you don't see that. And so this is why particle and cell, it basically subdivides your volume. It says, yes, we look at the average, but we look at the average in different volumes, or for different parts of the plasma. And then again, you can resolve the plasma dynamics. Is that what you were referring to?
Well, my question was more or less referring to the fact if you don't account for any interactions between the particles, which you don't have, if you say left side of the Lassov equation equals 0, then how does anything interesting happen? Why don't just the particles move with a constant velocity in each direction?
But we do account for interactions. It's just a different type of interaction.
But where does it come from?
It comes from the Maxwell's equations. So it's one thing to say you don't account for like individual particles colliding. It's another thing to say you have charge separations, and that's also a Coulomb force. Yeah, and then you get interactions. Anything else? Questions are very welcome. No? Okay. Then let me move on with very interesting physics, which is magnetic reconnection. So this is actually the astrophysical phenomena we're interested in. So it happens on the surface of the sun, and this is such a picture from the surface of the sun. And maybe sometimes in a movie you saw that, where you have these loops of plasma, and then they do some stuff, and then it flies out in space. And most likely, the dynamics responsible for that is so-called magnetic reconnection. And what happens there is, if you zoom in into these loops, what you get is these black lines are magnetic field lines, and then the red color is supposed to be the plasma density, and this is what it's approximately supposed to look like. So you have magnetic field lines, which you see, they go like this, and actually they go in opposite directions, and when they get close enough, the idea is, which is not actually what happens, but the idea is that they merge and then they reconnect. And so you have this motion of magnetic field lines coming together and shooting to the outside. And that happens repeatedly. And actually what people found is that it gives you very high energy particles. For some reason, this mechanism, which is also not fully understood yet why it does this, through this behavior, it generates particles at very high energy ranges. And so let's look at it in more detail. How do we simulate this? Well, what happens is the following. Initially, you have a plasma in equilibrium state. And what that means is that for a 2D system, which we're only going to consider today, a 2D system, you have the following expressions for the magnetic field and for the density of the plasma. And if you plug them in Maxwell's equations, you will see that this system does not evolve in time. If you just put in this magnetic field with this density and give this plasma some velocity, then your Maxwell's equations are not going to evolve in time. So this is what we call a steady state system. And so it's very stable, but then somebody, and I don't know who, found out, aha, let's add some perturbation, right? Let's add some tiny term which is going to disturb that equilibrium. And then you get exactly the shape of the magnetic reconnection I showed you before. And what's more, for some reason, this equilibrium system then explodes so much that you get this very high energy particles. And so this is what we do. Initially, we apply this magnetic field and particle density. We apply some kind of small electromagnetic perturbation. Most of the time, it's like some radiation coming into the plasma. And then you get a lot of dynamics suddenly, which accelerate your system very, very much. So what happens during that time? Now, what happens is the following. You have a lot of blue and red lines. So let's first focus on the blue dotted and the red dotted lines. And the blue dotted lines are the electrons, and the red dotted lines are the ions. And I said that these magnetic field, they merge together. And by merging together, because the plasma, it circulates around these magnetic field lines, it will be pushed into the middle. And so the ions and the electrons will be pushed into this central piece. But they will also be accelerated outward. Now, why will they be accelerated outward? It's because in the middle, and that you were able to see in the picture before, the magnetic field becomes zero. And so when you put a high density plasma there, it will go into these opposite directions. So that's one part of the dynamics, the plasma moving inward and then being ejected outward. And the other part of the dynamics is actually these blue crosses here. It says current. But what it also is that in the middle, because you get a lot of changing magnetic field, you also get an electric field. Because change in magnetic field over time gives you an electric field. And so this also accelerates your particles. And then finally, you have a lot of particles being accelerated in this almost circular motion. And because of these circular motions, you get an out-of-plane magnetic field. And so the takeaway message from this is that characteristic for magnetic reconnection, yes, it's that you have reconnection of field lines, but you also have this out-of-plane electric field in the middle. And on the sides, because of the circular motion of the charged particles, you also have an out-of-plane magnetic field. And so if you want to look for whether our simulations were right, whether we're actually simulating magnetic reconnection, what we want to look for is we want to see, do we actually get this out-of-plane electric field term? And do we actually get this out-of-plane magnetic field term? And this is what you can see in these plots here. So this is our simulation. Very exciting, a lot of particles, accelerated on many GPUs. And you have these current sheets here. Now, what I mean by current sheets is that this kind of indicates you the plasma density or the charge current density. And actually, we have two of such currents. And this is has numerical reasons. I previously showed you only one, but we chose two because this allows you for periodic boundary conditions, and that is very feasible in terms of computation, because if you have reflective boundary conditions, your particles will reflect, and that will give you weird stuff in your radiation. And so, therefore, we employed this two current sheet system, but again, I'm going to go back to the one, displaying you only one current sheet, because it's just more interesting. And this was just a side note for you to know that sometimes we also have to fiddle a bit around to make radiation calculations possible. And so let's look at one of those current sheets and look at how it evolves in time. And you will see that, for instance, this plot here, where the color indicates the out-of-plane electric field, we're exactly in this region where the magnetic reconnection happens. We get this out-of-plane electric field. And similar thing in the plot above, which indicates the magnetic field, it gives you an out-of-plane magnetic field, as we would expect. So this kind of goes to show, indeed, we simulate magnetic reconnection, but it also tells us, well, what do we want to look for when we look into radiation? Because the radiation will come from accelerated particles, and to understand where this radiation comes from, we need to know what is actually responsible for accelerating your particles. And so this leads us back to what I said, responsible to a big extent is this out-of-plane electric field. And then we can think about it in a bit more theoretical terms, because we say, aha, this electric field, it accelerates the particles in a so-called power law. So here you have on the x-axis your energy, basically, and on the y-axis the particles, which have that energy. So it's a histogram, and it's in log-log scale. And you can see, for instance, especially for the violet curve, that there's some region where the particles, they follow a straight line in the log-log scale, and a straight line in the log-log scale is a power law. So something which scales like x to the power of minus alpha. And so we say, okay, we know acceleration happens by an electric field, and then once that happened, we know that the particles follow something along e to the power of minus alpha, and they gyrate in a magnetic field, because that's all that's left, right? After the particles are accelerated, there's not much dynamics going on, and so they're just chilling in the magnetic field. And so we can think about this theoretically. Or I was supposed to think about this theoretically, but actually, this is something else. Now let me skip forward maybe to the theory part. Okay, because this is more interesting at the moment. Now, the way to think about this theoretically is the following. So, as I said, we have this acceleration through electric field, and so by using some formulas, which are actually just basic electrodynamics, we can derive a term of how the emitted radiation energy is going to look like with respect to time. And we can do the same thing, again, with basic electrodynamics, by looking at, okay, now after the acceleration, we have a power law of particles, and then some energy is going to be emitted in terms of radiation. How's that energy going to look like? And that actually scales linear in time. And that is great, but you can also see something else. In this formula, you have a lot of constants, but you also have this epsilon. And what this epsilon is it's basically the magnitude of the electric field which was responsible for the acceleration. And here you have something else again. You have the magnetic field in which the particles gyrate in the end. This alpha comes from the power law of the particles, and that we can retrieve. It's not important how, but we can find out what it is. What we cannot find out is the n. So the number of particles is also a bit arbitrary, right? How are you going to define which particles are like part of the motion, which are not? It's like there's no hard cutoff. It's a continuous thing. But we can also get rid of it, because we know, well, all the particles which were accelerated by the electric field will eventually be in a power law spectrum. And so we say, aha, when we have the energy from those two events, let's just divide them one by another. And what you get is just constants and the electric field squared divided by the magnetic field squared. So you get this ratio of very, very fundamental experimental values, which you cannot probe because the sun is very hot and you cannot just go there and try measuring an electric field. So I get these very great values just by looking at the radiation. And so that is what made us very excited about, okay, let's try and see what we can get more out of radiation, and let's try and see whether we can actually test it and say, okay, guys, we calculated something now. Experimental people, please help us. And we were not the first ones to think, aha, maybe radiation is interesting, but we were certainly the first ones to think about it in these terms. Somebody else called Zhang previously worked on this, and he actually examined blazars. So blazars are just very high energy phenomena in astrophysics, But many think that the reason why they're so high energetic is magnetic reconnection. And then he said, well, then let's do the trick that we're actually doing right now. Let's measure the radiation in a simulation that comes from magnetic reconnection. But he simplified his things again. Again, now a bit of advertisement for PIConGPU. We have high-performance classes, a high-performance code. We can do a lot of expensive calculations. He couldn't. So what he did is he said, yeah, the radiation is going to be approximately synchrotron radiation, so everything that we're going to see is just charged particles gyrating in a magnetic field. And that is going to give us radiation. How do we calculate it? Well, we look at a certain region in space, say, we have an average magnetic field there, we have an average particle energy there, it's going to give us this average energy. And then you do it for a lot of field positions in your space. And that gives you kind of an average energy, but also not the full story, because it's just gyrating particles in a magnetic field. And also, he only looked at the out-of-plane direction. So he only looked at it from one direction, but not every direction as we did it in our calculations. But he still found some very interesting things. So first of all, something to be expected is that the radiation flux, it peaks when you have magnetic reconnection. Well, why is that expected? Is because you have a lot of particles being accelerated very much. And so, of course, this is going to give you a lot of radiation. And so you can see that once this happens, you get a peak. And this kind of tells you, aha, there was some high energy phenomenon. Then he did some examination on the polarization degree. So when you measure all the light you get, how polarized is, like what percentage of light is really polarized. But for our examinations, this is not too important. But the other and really most important thing he observed is that actually there is a feature which uniquely determines magnetic reconnection, and that is that if you look at the polarization of the radiation you get, it swings. So once magnetic reconnection happens, if you start with like 90-degree polarization in your light, it suddenly drops to minus 90 degrees. And that's great, because when you get like such a random radiation swing, you're gonna be like, okay, that's interesting, that's very notable, that's not some random feature. But moreover, he was able to explain that. He said, well, most likely the swing in radiation, where it comes from, is because you have a lot of magnetic field lines changing. And when a lot of magnetic field lines change, the direction in which your particle emits most of its radiation, it's going to also change. And so this is why the polarization kind of swings. And so this is exactly what you see here, right? Starting from 90 degrees going down to minus 90 degrees. And this is an important feature which you should keep in mind, because it's also a good benchmark for us, right? So there was something found. We have a more complicated model. To make sure we actually have a valid model, let's kind of try and check this. Okay, and this allows us to actually come to what we've done. So this is the grand finale. We've simulated radiation spectra. And one plot you might be familiar with is the following. So on the x-axis, again, you have your frequency. And here the plasma frequency comes back. So it's omega 0, we call the plasma frequency. Again, it's why do we plot it in multiples of the plasma frequency? It's because initially your plasma was in thermal equilibrium and it was oscillating with this frequency, which is why you would see a peak at this frequency. But then above and below this frequency, you also have a lot of contributions. Sorry. And this is this classical plot, right? On the x-axis, you have the frequency, on the y-axis, the intensity. But this is not the full story, because magnetic reconnection has a lot of periods in time. So first, you have this equilibrium current sheet, which is disturbed by some signal. Then it gets out of equilibrium, it starts some motion, and then finally your plasma is accelerated to a power law. So just looking at a single spectrum will not be enough. You have to look at a lot of spectra in time. But such a plot, it's not very nice, right? Like, what are you going to read out of this? So instead, what we do is we do not look at this classical 1D plot of frequencies. We look at the 2D plot, where now the color gives you the intensity of radiation you get, the x-axis gives you the frequency of radiation, and then the y-axis is the time. And maybe one interesting thing to note is what I said in the very beginning. Remember that when you have any radiation, that is emitted below the plasma frequency, you won't be able to measure it. And of course, we can calculate it, but measuring it is a whole other story, and this is exactly what you get. So anything below this plasma frequency in an experiment, you won't be able to see it. We have some interesting signals there, which we're going to talk about briefly, but anything else is actually more important. And this is all observed at an angle as above. Now, it's not, the raw numbers are not very interesting. I can tell you what this angle physically means. And if you have your current sheet going like this, so the particles moving in this direction, you're actually looking at it from this direction. And yeah, so let's talk about what we actually see in this plot, what's interesting. Now we see multiple features, and let's start with the one we're not going to actually be able to observe experimentally. And it is this very faint frequency right here. So this faint frequency we know is the gyration frequency of the electrons. So when you place them in homogeneous magnetic fields and they circle, you can calculate that very easily, but you will also see that once we look at the polarization, that this signal is very polarized, which is an indicator for that it comes from a magnetic field. But also the fact that it's faint tells us that it must be this frequency, because faint means not a lot of particles are doing this motion. And you remember that the density was kind of this sec squared shape. So the further you go out, the less particles you'll have. But at the same time, the magnetic field was increasing the further out you go. So if you want a very homogeneous magnetic field, you'll have to go out very far. And in this very far region, there's not a lot of particles. But actually, in our work, we set a limit on when you can observe this gyration frequency, which would be great, right? If you could observe this frequency, then you could immediately calculate what your magnetic field was. And there's some mathematical tricks where you can get the plasma density from that. And that is pretty cool. But for that, we found out that your temperature would be higher than the rest energy of the electrons. So that's very high. That's 511 kiloelectron volts. And you saw that the room temperature was kind of 10 to the power of minus 2 electron volts. But in some systems, you can have such a temperature. And then you might actually, in another work or simulation, care about, if we employ such temperatures, can we see this gyration frequency? Okay, but that is more of a motivation if anyone wants to proceed on this work at some time. Another thing is this sink shape. Now I'm going to talk about it later in more detail. But basically I said, at the plasma frequency we're going to get some radiation contribution because that's the oscillation frequency at which the plasma oscillates in thermal equilibrium. But you can see that we have a lot of lines next to it. And it has the shape of a sink, so over sine of x squared divided by x squared. And why that is the case, we're going to talk about in the next slide. And then finally, the other very important feature is that once you go above 30 plasma frequencies, the radiation contributions, they start increasing. And you can see that very well on this plot right here. So here you can see the orange line is anything that happened before this point in time where your radiation starts increasing. And then after all this happened, you have something that in the log-log scale looks approximately linear, right? And remember, I earlier said, in the log-log scale, linear means a power law. And, well, where do we know that a power law comes from? The power law comes from the particles which are accelerated to a power law. And that is great, because we kind of get a hint, probably this point in time is the time where your particles are accelerated to a power law. And indeed, we can cross-check that with the simulation. We see, yes, that is the point in time. And we saw it just through the radiation alone. Okay, so now let's go back to the sink square. Well, what is a sink square? A sink you get when you Fourier transform a box. So imagine you have a signal that is very limited in time. So a signal that starts here and ends here and nothing else. Then if you Fourier transform that, you get a signal that is exactly the shape that I showed you earlier. Now, if I take a cross-section of the radiation I showed you earlier, this is what I get. I get exactly the sink square shape. So this tells us, okay, this shape most likely came from the fact that the plasma frequency was emitted only at a very... It was emitted only in a very limited duration and time. And that is exactly because of the fact that we put a disturbance term into our simulation. Because your plasma is in equilibrium, then the disturbance term comes and suddenly everything gets out of equilibrium. Now I have to go a bit faster, so let me just go very briefly over the polarization features. And for that we need the Stokes parameters, and actually in that case only the parameter Q. And the parameter Q, it doesn't matter how you calculate it, it gives you an idea of how linearly polarized your light is along the axis you're looking. So Q ranges from -1 to 1, and the more it goes to 1 or the -1 range, the more you know, aha, this light is very polarized. And so we can look at the same frequency spectrum as before, and you can see right away that the striation frequency, it has a very strong linear polarization. And at the same time, we see that indeed there is some region in the frequency where you go from very blue to very red, which means we get exactly this polarization swing which Zhang observed earlier. Now, and the same thing you see up there. This is now observed from a different direction, but you see that the polarization swing there is even stronger. And that indeed kind of, first of all, confirms our and his, or verifies the observations. And also, the light is very polarized, right? So again, I said that this was an indicator of strong magnetic fields, and we know, okay, this region, which I earlier said has a power law, indeed probably corresponds to the power law-shaped energy distribution of particles gyrating in a magnetic field. And yeah, this is, by the way, the polarization swing. From this, we can take the energy which was emitted in that frequency region, and I told you earlier that indeed the energy will scale with the time to the cube. And then once the particles are gyrating in a power law, it will scale linearly, and this is what we see in the simulation. So indeed, the model is to some extent verified. We're going to look at this in more detail. We're going to see how we can retrieve the quantities of importance that I stated earlier. But this is the first verification that we actually see that what we calculated is kind of true. And so to just give a brief summary, indeed we found the polarization swing that Zhang observed, but we actually saw that it was limited in frequency. It was only visible after 30 plasma frequencies. Then we found various characteristic frequencies. We found the sync shape and the gyration frequency. And exactly this sync shape was kind of characteristic for reconnection dynamics because it was this suddenly disturbed system. Actually, what I would have told you if I had the time is that you can actually reconstruct some magnetic field shapes from observing the polarization. And finally is that we have these two equations which link only radiation data to very important quantities in your system. And that is very exciting. And so we're now hoping that we're going to get deeper into this, and finally, maybe one day we could confirm this experimentally. And I'm done. Thank you very much. And if there's time, let's talk about it later, if you have questions.